Okay, hello everyone. We're the Mosquito Drone Surveillance Group. I'm Ragad,
I'm Raina.
and we
Uh,
have Muhammad and Tushar online.
If this works, that'd be good.
Okay, so we wanted to talk about by the numbers quickly to reframe why this is important. So based on some of our calculations, we calculated that there's about 120 million mosquito bites per second. And that vectors, yeah, and that vectors such as Aedes albopictus are expanding their habitats. So in the past 5 years, they've spread by up to 93 miles per year in Europe, which is much more than the past, basically as long as we've been collecting data. And currently about half of the world's population, so about 4 billion people, live in dengue risk areas with an estimated 100 to 400 million infections per year. And for West Nile surveillance systems, the average cost per one single mosquito trap is about $72 per week per unit, which obviously is not sustainable.
So that led us to come up with our need statement, which is a way to conduct low-cost, durable mosquito surveillance to obtain geo and temporal tag data in less urbanized areas to enable continual monitoring of mosquito populations in low-resource environments. And John's just going to talk about our thought process. Oh, wait, before that, we should also talk about what people are currently doing, because clearly, if it was sufficient, we wouldn't be up here in the first place. So traditional field surveillance is great. You just use standard traps, you test trap mosquitoes. It's direct field interaction, and so you actually get a lot of data from people working there who have expertise in this, but time and labor sensitive and limited spatial coverage because people can't be everywhere. And it's high cost to sustain, see previous point about $72 per trap per week. And it's not scalable to a national level, given that you need equipment, labor, and expertise. Predictive modeling, I personally love this, but it isn't ideal because you have to use environmental, climate and case data to forecast mosquito abundance, proactive and large-scale coverage, but predictions rely on data quality and model assumptions. And as we just discussed, if climate data is going to become less available, this kind of goes out the window. And it has a moderate cost because you need computing resources and expert personnel. And finally, you have mobile apps like Humbug, which is using citizen science to detect and identify novel species using smartphones, wide reach, low scale costing. But there is a participation bias because only like the people in this class, like us excited little nerds, will actually go out and do this kind of things. It's not very accessible to the general population. But again, it's still pretty low cost because app maintenance and development are inexpensive, but the main constraint is participation.
Yeah, so some of the things that we wanted to keep in mind, like for our benchmark table, we wanted to make sure that we would be able to capture mosquitoes using, just capture mosquitoes in general in a way that wouldn't damage their morphology, because we'd be doing like visual classification with like images or just like mosquito or bug scientists. Relatively cheap cost, preferably less than $60 per unit. We want to ensure, so like the concept was like a drone that would be able to catch the mosquitoes. So we wanted to ensure long flight, minimal trap drag. So we didn't want the trap to be too heavy. And then the imaging part wasn't something that we got to like for the purposes of like this class and this project, but that would be like something to consider.
And already there are systems that
And
Yeah.
there are a lot of systems in place.
centralized that.
So we wanted a controllable drone that would generally fly at low altitudes, and the idea was kind of that the air coming in from the top of the drone would kind of suck in mosquitoes, and then there would be some kind of trap along the top of it to capture mosquitoes in some way. And then we would be able to, so mosquitoes take it to some like center for classification, and like that would be used to monitor mosquitoes in different areas. And then a more advanced version of this would also have things like GPS and like spatio-temporal data to like better map these things out. But yeah, so that's like the general idea. And then
So basically as John mentioned, what we wanted to do is take advantage of the fact that drones, as they fly, suck in huge amounts of air in order to stay afloat and push that air out downwards. So this is a model we found of a drone similar to the one we're using. As you can see here, the air on top is coming down at a speed of about 5 meters per second, which is pretty ideal for us because considering, well, you can go to the next slide.
Should I play it?
Yeah, we can play it. So basically we used a drone and
Like drones in classrooms.
a humidifier to test the
You're a
air,
good flyer, it's okay.
to test the airflow. And as you can see, the mist.
So that people can see there's a mist coming out from the
Yeah.
humidifier. If you look
Wait, let me play it
closely,
again
You can see the
that's just tricky.
mist
Yeah.
more now, but
over here.
it conveys the same like patterns you would expect it to as the airflow mapped out in the previous diagram, which was really useful validation for us.
Yeah, so we were basically trying to test at what angle the airflow continues to go downwards as opposed to start getting pushed down. And here, wait, let's see if we can pause it.
So there's a capture cone around it.
Yeah, basically. And so around this angle and a little bit lower is basically the limit of what we'd be able to cover. And so what we realized is that basically it's kind of a dome-shaped area on top of the drone. Here's our little cute drone. And so this kind of area is where we'd be able to capture the mosquitoes if we were to deploy a trap on top of this. And so the next challenge was to design a trap such that it would sit on top of the drone in the ideal area to catch the mosquitoes without disrupting the airflow of the drone itself and preventing it from flying.
Okay, this is looping forever. There we go.
And so first we wanted to do some quick mathematical de-risking with Stokes number. And so Stokes number is basically a model to predict how particles are going to behave in a fluid. And so here, I'm not going to go through all of the calculations, but basically we wanted to predict if the mosquitoes are going to actually collide with the trap, or if they're just going to be blown off the sides or into any of the holes that we pierce within the trap. So obviously, if we have a trap sitting right above the drone, we wouldn't want it to be completely flat, and so we did some piercing, but we wanted to optimize how big the holes need to be in order to allow maximal airflow without letting the mosquitoes escape. And so what we settled on here is about 2 centimeters, as you can see over there, for the hole to prevent the mosquitoes from escaping and still allow the drone to fly. And based off of this, began to iterate off of different designs.
Yeah, so the first thing that we tried was this. We were basically just like kind of going around the dorm and trying to find things that we could use and put together because we had pretty limited time. But the first thing we found was this like porous, like clothy paper. So we stabbed a bunch of holes in it. We started with pretty small holes and kind of just expanded them like as we kept trying. And yeah, we could play a video of us trying to fly it. These were like kind of the biggest holes that we ended up like piercing throughout it. And you can see it's like moving a little along the ground, but not very
It's
much.
unable to
And-
lift
and
off.
It wasn't able to lift off.
Wow. Okay, this is a poor quality drone. We should improve.
Yeah.
Yeah.
That-
Yeah, this is a $40 drone from Amazon.
Yeah, so that failed.
I think, it's possible to find lighter materials, but
Yeah.
we can also up the
Yeah.
game of the drone
Yeah.
too. So I think this is just what we have.
Yeah.
So a second thing that we tried, based on a suggestion from Manu, was the drone came in a little styrofoam box that was already kind of in the shape of it. So we kind of cut it and then put holes on the bottom and kind of put it on the drone as if it was like a little helmet. To try to see if that would work. That very similar. It did not lift off the ground. Maybe the holes needed to be bigger. I don't know. We didn't have a lot of faith in that concept, to be honest, but we tried it out, and yeah, I think the clock one from the first design moved a little bit on the grid. I think that one was a little bit closer, but this one didn't really move at all. So yeah, no airtime.
So then we moved on to design 3, which I'm sure some of you guys saw us tinkering around with in class, which is like basically we had this and we had these insect traps that John was able to procure from a little lab. That was sticky. Do you have one of the perfect? We'll pass one of those around and we just stuck it on top of this. Yeah.
Yeah.
And so we designed 2 platforms to elevate the trap. And
Don't stick yourself.
yeah, don't stick yourself.
Very annoying.
It's very, very effective, I will say. And yeah, so we made these 2 platforms, as you can see on the drone, and this is to create distance between the trap and the propellers, because we also noticed that when we were using the porous material from design 1, some of it was getting stuck in the traps, and then it had no chance of getting off the air in the getting off the ground in the first place. And then the typical sticky bug trap, we cut it into a 9 by 10 centimeter piece, and adhere it onto the platform. And it flew. And we got a bug around Lake Lark, which was really great to see.
That's a giant bug.
We got a really heavy,
That poor thing.
yeah, it is not a mosquito, as you can see, but we got a bug, which is great, given that this drone is not the best. Yeah.
Kind of like when the LED, the laser went down. It's good.
Yeah, and so we have an actual video of us like flying it. This is not,
That was the test flight.
that was a test flight near Lake Lark, because if we were flying it over the lake, we didn't want it to go down before we were confident.
Is there water right now? Yeah.
In
A
some
little
parts,
bit.
yeah.
So we went closer towards the areas where we could hear the water and the frogs, because we assumed that'd be like
Oh,
generally better for bugs. And then this is the time we were
It's
actually,
also good that you're doing it at night.
Yeah.
because a lot of
Yeah.
Surveillance at night is important.
Yeah, and also the drone has, as you can see, like a lot of light. And so we turned off,
Good as an attractor.
yeah,
Yeah.
so we turned off the flashlight we were using at some point and just flew it around for like 10 minutes, 10, 15
So
minutes.
you don't actually know when you caught the bug.
we aren't
That
too
it
sure.
just Came back, so it's true surveillance then.
But
Yeah.
it was some point at the end because we did try like two or
3
yeah, two or
locations.
3 different spots.
Yeah.
And so like we were looking at it in
What I'm
between,
trying to say is,
but
it doesn't work if you're chasing an insect. No, I
Yeah.
was just flying around, you brought the thing back, and there was an insect. on it.
Yeah. It was interesting because in like the first 2 times we flew it, we just caught like stray bits of grass and things like that. And then on the 3rd time, we were like, is that an actual insect, or are we just hallucinating it from happiness? But
Yeah.
it was an insect, which was really great. So our next steps, Ragad, do you want
So basically, the green lacewing, which is the bug that we caught, as you said, is ginormous. So
Yeah,
it's
that's
large.
why it caught on it.
Yeah, so its larger size might have contributed, yeah, to basically like a higher Stokes number. And that's why we caught it. And so we're thinking that since it's about 5 to 10 times larger than a mosquito, perhaps using that to scale down the size of the hole that we created and increase the number of holes so that we don't disrupt the airflow.
We can, best of both worlds could be, what if we had parallel plates?
Yeah.
Where the
Close.
flow would still go through, but the plates are close enough that you would trap, rather than a mesh.
As in like next to
So
each other.
rather than sticky paper stuff like this, where you actually get flow diverted, you can have them like parallel plate capacitor. They are this way, the flow is still passing through it. But then you're just getting the things and wings getting caught in. So anyway,
Yeah.
it's just, there is so much space in geometry. I'm saying mesh is not the only architecture.
Yeah.
And I think we should upgrade to another drone.
Yeah. Yeah. Our drone only reached on Monday, so whatever testing we were able to do was in the last 2 days. So we are very happy we caught a bug.
Yeah, so we think its larger size might have been the reason we were able to catch it. So we're thinking of how to maximize Stokes number, basically decreasing the puncture size or increasing the number of punctures or different geometry as you were mentioning. And also perhaps testing a lightweight steel mesh like the kind that's used in like tea strainers could work, dipped in some form of sticky substance like honey. We wanted to use honey on the paper mesh idea, but since we couldn't get it off the ground, that was kind of out the window. Yeah, and also test other materials for sticky substances and see what ideally catches the mosquitoes without destroying their wings so that we can identify them later. And also try for longer flight time, 20 to 30 minutes perhaps or longer based on the battery life of the drone and see if we can catch more bugs and learn from that. So,
Thank you. Any questions?
You guys were perfect in timing. We have a minute for questions. Questions? Yeah.
Like where's the for example, if you have light knowledge, some streamers like to be like protein access. Also, another question is, can you design some like moving trajectories so that it creates some vortex so that traps like response things?
yeah, so your first question is about light, whether light would be helpful.
Yes.
Yeah, I mean, the drone does have like the LEDs on it, which we think might have been helpful for attracting the bug.
And all classic mosquito traps have light.
Yeah.
Yeah.
CDC light traps. So light is a common criteria that's actually used.
Yeah, so that was part of the reason we picked this drone because it has those lights around the propellers.
Also, we can see it in the night if we're flying it.
Yes,
Yeah.
that too. And yeah, I think definitely creating like some form of vortex that directs the mosquitoes down onto the trap would be the ideal scenario here. So that's why we were thinking of like testing different geometries and shapes to see
Yeah, I
what
think it's a little bit tricky because one of the challenges is you have to understand the physics of the drone very well because the drone is both an suction mechanism and a repulsion mechanism. Anything that you generate, insects are very sensitive to turbulence and different insects have different turbulence. So gnats are a good start because gnats swarm. So you know that if you pass through that swarm, there's a certain possibility.
Yeah.
But it would be valuable to first test, just like when you look at these collective fish in the ocean, but when a shark tries to come through, the entire collection splits. Because hydrodynamically, they can actually sense something coming in. So it's more complex than that. But the best way to do it is to find a gnat swarm, which I think, summer is coming. So you guys have plenty of.
Yeah.
You cannot say after that many mosquitoes and insects being present, we have to be able to find insects.
Yeah.
Yeah, whether it's on campus or some other places. Okay, any other quick question?
Yeah.
When you do your flight, do you think there's like, are you going for like a random flight pattern, or do you think, or are you going with like, what type of flight pattern basically? Yeah, the grid search, maybe just random, just because maybe random is. Say a random selection.
I think what we were focusing on is staying low because since the suction is happening from the top and most mosquitoes fly at about like 7 to 10 meters, staying low is ideal. And also what we were trying to do is fly low and then move higher in order to attract mosquitoes from different areas. So I think that was what we were thinking about mostly. And in the like area that we were in, we were kind of just going like for lines.
It's like a reverse diving technique. It's like
Yeah.
an owl.
I think we have 3 people heading out to a couple of very heavy mosquito sites. Hope is heading out to Nigeria in a month's time. Pranav is probably heading out to Liberia pretty soon. We have an India field trip. You guys should find definitely a place. This is a very straightforward test. I think it's valuable to do it with the physiology of the mosquitoes themselves. That iteration. So find California. What is the hotspot of mosquito? Take 2 days off. Go out there and actually do it with mosquitoes. Before designing many other things, you need to test something.
Yeah.
All right, I'm done. So let's keep going.